doing a set of experiments to try to determine something called the point spread function of fMRI, of the bold response. So there, this is this Maastricht? I wouldn't be surprised. Oh, it's Utrecht, actually. That's interesting. So this is a point spread function of the bold response across columns and cortical depth in the human extrastriate cortex. So the extrastriate cortex is part of the visual cortex. Do you guys know what cortical columns are? This is one of my favorite papers. So János Zendegothai was a Hungarian neuroanatomist, right? So this is basically, I think that's, yeah, this is a cortical column. And basically you can see that there's, you have, so layer 1, layer 2, layer 3, layer 4, layer 5, layer 6 of the cortex. And then this is a idealized cartoon, basically, but it is based on, I think the visual cortex most likely, because that's what we know the most about. So the cortical column width, cortical column width is about 300 microns. And then the thickness is the thickness of the cortex, which is probably no more than 1 millimeter, and frequently it's close to 0.8 or 800 microns or something like that. So this could be thought of as a representative processing unit of either input, if you're measuring in the center of the processing unit, or output, depending on where you're looking at this. But again, the cortical column is about 300 microns in diameter, and it extends throughout the whole cortex. Cortical afferents come into, this shows you basically the arrows of where everything goes, at least as they knew it in the 1980s, which was pretty good. So the idea is, do we have enough spatial scale to see cortical columns using functional MRI? At 3 Tesla, you don't. We can say that. At 7 Tesla, you start to be able to see. So they're looking here in this study in V2, which is the secondary visual cortex. And there are stripes that are basically, related to each other and tuned for certain features like edges and things like that. So let me get to some figures that make sense. So in S2, you have these pale and thin, so you have magnocellular LGN projects to thin pale areas in S2, these vertical stripes, or V2 and vertical stripes. And then the parvocellular area, the lateral geniculate nuclei in the thalamus, which is where, so the LGN is where visual stimuli arrive after the optic nerve. So the optic nerve feeds into the LGN, and then, the magnocellular and then parvocellular are different stainings, but they actually turn out to be, important for the processing. So what you see here is that each of these, the dark rows, so the thick and pale rows, which are, you can see here, are coded by the magnocellular, whereas the dark parts are coded by parvocellular. And there's been an enormous amount of research on this. So we know what visual stimuli we can present to people that are going to elicit responses specifically in those neurons. So concentric circle grading of either 20% contrast, the contrast polarity reversed at a temporal frequency of either 1.5 or 7.5 hertz. The two stimuli alternated in a block design, so they're trying to, so a block design is where you're sort of maximizing your signal to noise if you have a simple paradigm, but it's not really realistic. And then, the subjects were told to fixate on this dot throughout the whole time. And if they did that and they see this thing alternating back and forth, it's going to light up these two different areas of the visual cortex, which are basically alternatingly. And this, allows you to extract the signal in a reasonable way. So we want to look real quick at the MRI. So they're just looking at the visual cortex. So 0.9 by 1 millimeter is, and this is on a 7 Tesla scanner, so they can do that. And then high resolution T1 was, they don't even tell us, do they? Oh, we would have to calculate it from this. So it's, they're 0.5 millimeter isotropic. So we're looking at 500 micron isotropic. So it's pretty high resolution. It's not down to the cortical column, which will be 300 microns in diameter, and then like a millimeter thick. But you can see that, they're doing pretty good. This is a pretty high resolution image. Let's see, what does it say? You can see what landmarks indicating locations within or outside the calcarine sulcus, which delineates V2 approximately. Co-registered EPIs. Let's see, what is it? E. Mean 3D EPI image superimposed with a coherence map from the stripes experiment. So you can sort of see that they're looking at just cortex, and there's some coherence differences. And so they basically end up with this image. And this is their resolution. So you can see once they've done some processing on it, they're getting down to about the millimeter. And you can sort of see these cortical column stripes. So in the visual cortex, they look like stripes because of the way they're organized. Again, you can see the cortical distance that they're looking at on this point spread function really is 1 millimeter. You can see the difference there. It's not super great. Now they're going to try to convince us a little bit more with some better phase coherence maps. But again, you can see, you go from 0 to 1, or you reverse the signal within 1 millimeter. So that really gives you might get down to 500. So, you might get down. So this is 2 millimeters actually, because you're going across -1 to 1. And then you might get down to 0.5 to 0.5. So this is the maximal spatial resolution really of MRI, a functional MRI. I've seen some in animal studies, you can get down lower because you have much higher Tesla magnets. But in humans, basically, we're looking, these are the cortical columns or the stripes within V1 that you see that are basically what they are. They're all those types of cortical columns that respond to that certain stimulus and firing together. So you can see that. Pretty good. But again, your resolution is maybe sub-millimeter, maybe, but not close. And so if the cortical column is our target, this falls about 10 times short, volume-wise. because you got to think about these things in volume. You can't think about them in just two-dimensional space. So if your cortical column is 300 microns across and you want to look at layers 1 and 2 responses versus layers 5. So 5 is the output layer, or I think, yes, the major output layer. So, you want to put output versus input, you've got to be able to cut this column somewhere and look at certain groups of cells. And so with human neuroimaging, we're still bleeding over a couple of these columns. And this is pretty much maximal resolution, I think, without like going to more experimental approaches. But that's one theory. It depends on data processing ultimately. But the nice thing to know is that really you just need to get down to about 0.3 microns cubed to do the job, which we're getting close to, which is really kind of interesting. Again, you're looking at blood flow, so there's all of this smearing. We'll see what the new magnetic devices do. Now, neurosurgeons they don't do this as much as they used to, because there are more restrictions on it. And there are far fewer people getting epilepsy surgery, quite frankly. When people have epilepsy, they have to sit there for 2 weeks in the epilepsy monitoring unit, or at least 1 week, so that they can collect enough data to catch a seizure. So they take them out of their meds. They sometimes stimulate their brain a little bit. They do some tweaking. And the other thing is that they don't want them to have a really bad seizure, because then, one, they're not going to collect their signal, and two, it's medically problematic. You can have problems from having a very strong seizure. So, but we've done one experiment where we had depth electrodes in a participant, and we're using laser pulses. And with the depth electrodes, you can get down to the size of a cortical column. You can theoretically get down to neurons, but again, your spacing is more like 0.5 millimeter. So your resolution isn't great, even though. And the other thing is that you're not going to put electrodes all over somebody's brain, because these electrodes are. The old ones were 1 millimeter thick. And so, you'd have to open the skull, you'd locate where you're going to put in these electrodes. And now they put in a stereo electrode. So they put, a group on one side, a group on the other. And, it's not like they don't do any damage. They do damage. The newer ones, I think, are probably far thinner, but still you're talking about 0.5 millimeter. And I remember when I was taking my cerebral cortex class, everyone was like, well, what's your favorite part of the brain? I was like, well, which one would you like to do without? There's not many parts of your brain that you just want to be like, okay, fine. I mean, like if it's disease, yeah, you take it out. If you've got Parkinson's, you eliminate the ventral intermediate nucleus, and you don't have such a tremor anymore. But it's not, people don't voluntarily give up their healthy cortex, and for good reason.